On behalf of NADCL, on behalf of organizing community, and on behalf of students, we welcome you again. Ma'am, please continue.
Thank you, Dr. Hamida. I'm glad. Thank you for the kind words. So, I am basically by profession a fisheries economist, and knowing that the audience is diverse here, so I believe that people from agriculture and veterinary background as well. So I would like to just start from the basics because I don't want to bore people, because most people feel that statistics is kind of a dry subject and a little boring. So just to make things interesting, I have just given the basics only, which of course both biological scientists as well as social scientists need in their day-to-day this work. So be it in a research proposal or student-related research. So these things are very important. So, just to give you a brief intro about the data analysis and the main tools that we use. But before that, I would just like to brush up your concepts more on descriptive statistics, especially concentrating more on, say, standard error, standard deviation, what is the difference, then some basic graphical analytical tools which are used nowadays to see the patterns and plot your data in a more better way, so that it will be a better representation of the results. And then I have tried to give some basic information about the parametric and non-parametric tests which we use in our day-to-day life very frequently, and then some information about regression and correlation, and some multivariate tools which I will introduce here if time permits. Okay, so let's, without wasting much time, let's start. So, as the topic is basics of data analysis, so what actually data analysis means? So there are various steps whenever you plan a research. So first in our mind, we have certain research questions and a hypothesis. So for that, accordingly, the decision has to be made that what kind of the data you will have or you have to collect. So first process in this is data decision. So what kind of a data is required for fulfilling or answering your research questions or fulfilling your research objective or goal of your research. So accordingly, we plan whether we will need primary data, we will need secondary data, we will need experimental data, that depends. Then after that, you have to go for data collection. And after data collection, I mean, with regard to social science, we collect data. But in case of biological studies, you conduct experiments, and the experiments also generate you some information in terms of data. Now, the data is actually a raw information. So what to do with that raw information? That then the story of analysis starts. So, but before doing any kind of analysis, you have to make your data ready. So ready in terms of how clean and smooth is your data, and whether the analytical tools will work on it very efficiently or not, that we have to see. Then we go for data analysis, in which we apply various logical techniques which try to describe, summarize, and compare the data. And of course, depending again upon your research questions, whether it's a predictive kind of an work where you want to predict something, or you want to estimate certain parameters, or generalize your results from a sample to the entire population. That depends. So based on this, we have different types of data analysis. So we have basically 4 types of data analysis. First is descriptive. So descriptive tells you about, it summarizes the data. For a particular specific period of time, what are the characteristics of your data? Then diagnostic analysis, or we can say inferential analysis, which makes you understand by drawing connections between various variables, which you can, of course, generalize the results to the population as well, because we mostly take samples. Sample is nothing but a representation of your entire population. Okay. Then third one is predictive analysis. Predictive analysis, as the name indicates, means prediction. That means you are trying to use trends from the past data to anticipate the future outcomes. Then next is prescriptive analytics. Prescriptive analytics means simulations. See, we have sensitivity analysis, wherein you try to simulate different types of scenarios, wherein different strategies or policy related things can be suggested based on some simulations of different scenarios in your model. That depends again on your research background, whatever things are in your mind or whatever questions you want to answer. So before delving deep into the data analysis, first of all, the most important thing to know is what are the different measurement scales? Because of course, data is measured on different scales. So you have four major scales. First one is nominal scale, ordinal scale, ratio scale, and interval scale. So what does this mean? In order to simplify the things, the nominal means it's a string variable where only you usually name things. And it usually does not convey any meaning, but it is where there are categories and you name certain, like gender, male, female, then eye color. It can be brown, blue, green, black, whatever. Then ordinal scale is where things are ranked in order. That means there is a ranking or that order has certain meaning. So for example, low, medium, high, or how's your mood, happy, neutral, unhappy, or sad. Then comes the ratio or the interval scale. In the ratio scale, which is the most robust scale, we used for variables that have measurable intervals, for example, weight. And you have a meaning to the absolute zero as well in case of ratio scale. I will give you the examples further. So here, just we have given some examples from the fisheries sector. So first is nominal scale. It's a type of data is categorical because there is no order and there are no equal intervals. There is no true zero that exists in this. And for example, fish species. You have numerous number of species, you just name them. So that will be your nominal scale. Then you have ordinal scale in which the data definitely is categorical. There is an order, but there are no equal intervals and no true zero exists. For example, if you want to see the experience level of fishers, say beginners, intermediate, or experts. So there is a hierarchy. Some order is there, but there are no equal intervals or no true zero existing here. Then comes the interval scale. In the interval scale, the type of data is numerical. Okay, there is order also, there are equal intervals also, but there is no true zero. For example, water temperature. Water temperature, true zero means true zero does not have any meaning in terms of this. Then Fisher's attitude also. Fisher's attitude on a Likert scale, zero means nothing. That does not mean that they do not have any kind of attitude. So that is the meaning of true zero. Then for the ratio scale, everything is robust. It's numerical. There is order in the data. Then there are equal intervals also, as well as true zero exists. For example, fish catch. If fish catch is zero, means the fishers have got nothing in hand. Then a revenue generated. All those things are measured on the ratio scale. Then coming to the types of data, we have different types of data in our day-to-day life. We just need to categorize them. So based on the nature, we have qualitative data and quantitative data. So as the name indicates, quantitative data is something which can be measured with numbers. Okay, and it can be measured on two different ways, like discrete data. Discrete data means whole numbers. There is no scope of fractions or decimals. For example, number of items. I'll say 10 tables. I cannot say 10.5 tables or 3.5 tables. That doesn't make any sense there because as a whole number only, that has some meaning. Then continuous data can be broken down. For example, height, weight, income, where decimals also have certain meanings. So in the continuous scale, this data further we will break it down. As I said, the interval scale and the ratio scale, these things come under continuous data, under the quantitative category. Then qualitative data is non-numerical data. Of course, qualitative data handling is actually difficult. It seems easy, but it is not. Anything which can be quantified or measured, it is easy to do analysis with that. But certain things which cannot be quantified, but they have definitely a role to play. So that's why qualitative data handling is very tricky. So in the qualitative data, we have non-numerical data, like, for example, yes or no responses. We have a 5-point Likert scale responses or certain quantum scale responses, which we take mostly for behavioral parameters. Say we have attitude, we have perceptions, we have awareness about a certain issue. So all those things are measured on a scale. Fine, so that will come under qualitative data. And again, for the qualitative data, you have to use these two measures, which is nominal and ordinal scales. Okay. Then, based on time frame, we have three types of data, rather four types of data: cross-sectional data, time series data, and panel data or pool data. So cross-sectional data, please remember this, cross-sectional data is nothing but when we get the observations of certain variables at a particular point of time. Say, for example, the data that we collect, if you're going into the field today, and then I'm asking you, there are 10 households or there are 20 households, you go and collect their basic socioeconomic data. So at that particular period of time, for 10 or 15 variables, you will collect the data from these 10, 20 households. That is called as a cross-sectional data. But when you have data collected over regular intervals of time, say, for example, I will ask you, you take a 10 years data for fish production in a particular state, or you take marine fish landings of a particular state or of a particular district. That will be your time series data. The time interval depends. It can be daily also. Like if you, I will ask you to take the price of a stock, say HDFC Bank stock for last 1 week. So you will take data based on hours also, based on minutes also. So that time frame varies. It can be hours, it can be days, it can be weeks, it can be months, it can be years. But one trick here is that the lesser the lag between the time intervals, the more robust are your predictions. That's why in stock markets or in this financial kind of things, we mostly deal with an hourly or mostly hourly data, because they are really volatile. Then comes the third category, which is panel or longitudinal data. So panel data, actually, in simple words, if you will say, it is a combination of cross-sectional and time series data, wherein you have cross sections which are dependent on each other, but we take their readings over a period of time. Say the simple example is the census data. The census data is actually a panel data, and dealing with panel data is again very tricky. It is very difficult to do analysis when you have a panel data, but the results are very robust. And in certain kinds of situations wherein there are limitations with the cross-sectional data or the time series data, that time the panel data plays a very important role. Then based on data collection, as I said, we have two types of data, primary data and secondary data. Primary data means which you will go into the field and collect. Okay, so you are the first source of getting that information. Then secondary data is which somebody else has collected and you are taking it and using it. Say we have all the databases, we have NSSO databases, we have National Health Survey planning data, that also we use. Or say we have a handbook of fisheries statistics, or we have IndiaStat as a database repository. So from that we take data which has been collected by somebody else. Fine. So now coming to the analysis part, as I said, we will mostly touch about the descriptive and the inferential statistics. So descriptive statistics is the basic of any analysis, be it any data that you have to handle. We have to take into consideration the descriptive statistics. So descriptive statistics is nothing but wherein you just summarize the data based on certain characteristics. So it focuses on collecting, presenting, and characterizing the sample data. And it can be measured both numerically as well as graphically, which I will tell you further that how do we do it using graphs. And then conclusions are whatever conclusions you draw based on the summary of this data, it is confined to the only particular sample. You cannot generalize those results to beyond that sample. But in terms of inferential statistics, you predict and estimate. That means you deeply analyze the data, you take the sample, you estimate that sample based on certain observations, and then you try to generalize those results. For example, if your sample size is a good one compared to the population, then you can generalize the results which you have obtained based on that sample. So that kind of a statistics is called as an inferential statistics. And in the inferential statistics, the most important is the hypothesis testing or test of significance. That's why we use different types of tests. And of course, here conclusions are limitless and predictions are made based on the parameters of the given population. Fine. So now we will start with descriptive statistics. So just a brush up of the basic ideas. I'm sure all of you might be aware, but still there are certain confusions with regard to certain things in descriptive statistics, which I will touch. So basically under descriptive statistics, we have majorly three things to see. We have measures of central tendency. That means how your data is distributed in and around a particular position. Okay, then measures of variability or spread. That means how much variation is being explained by your data, and it is explained using range, variance, and standard deviation. Then we have measures of relative positions. That means skewness and kurtosis, that we will see in the upcoming slides. But you should know one thing is that we always try to do sampling in such a way which captures the maximum variation in the data. So whenever there are uh, causes of variation in the data, these variations affect what? These variations affect these three things. That is your position, speed, and shape of the data. And what thing explains that? That thing is explained by descriptive statistics. So when we collect data from a group of people, say that is your sample, the numbers won't be exactly the same, but they will often gather around a common value. So when you plot a particular data that you have obtained, you will see that there is some aggregation in the data. Around a common value, other observations will also stick. That common value is your central tendency. Now, depending upon the data, whether it follows a normal distribution or it does not follow a normal distribution, we can say that if it follows a normal distribution, that means that a central value will be your mean. And if it does not follow a normal distribution, then we can say it is median and mode. So now what is median and mode? Mean, of course, we all know it is the average value. The median is the middle value in a data. Okay, when you sort the data in ascending or descending order, whatever comes in the middle, that is your median value. If you have even number of observations in the data, then you have to take average of the two central values, which is your median value. And mode is something which is most frequently occurring in the data set. So with that also, you can judge. So these three are the measures of central tendency. And here, the mean is most robust. And that's why this is mostly used with all the parametric data analytical tools. And median and mode you will mostly find with non-parametric tests. Then comes the measures of dispersion. So this is important. So variation in the data is very important. How data points vary. As I said before, when you plot the data, you will see that there is some pooling around a common value. Now, how other observations are distributed or scattered around that common point, that is your measure of dispersion. So range, standard deviation, and variance. These are the three parameters which we study under dispersion. So range tells you the difference between the highest and the lowest value in the data. And standard deviation tells you the average distance of the points from their own mean. So how much the observations deviate from their own mean, that is your standard deviation. And variance is actually a square of standard deviation. It is a more, we can say, for the ease of convenience, we use variance. So a low standard deviation indicates that the data points are clustering around the mean, and a higher or a larger standard deviation means that they are scattered widely, but we do not want that. So what is most desired here is that a low standard deviation. That means your other observations in the sample are more or less clinging to the mean, which is good sign for us. And of course, for the population standard deviation, we denote it with sigma, and the sample standard deviation, we denote it with the small s. And this is the formula that we use for getting the standard deviation. And of course, it is a more robust measure of variability. So what is standard error? So in most of the biological studies, in nutrition studies, in health studies, in aquaculture related studies, you will see that in the data, which particularly the ANOVA, two-way ANOVA, one-way ANOVA, you have the values of mean values, and then next column is standard error, plus minus something. So what is that? And how is it different from the standard deviation? So here, the point, just to make things very simple, it is the standard deviation per unit of a sample. So that means how your sample mean of the data is likely to be from the true population. So mostly what we do, we take a sample because we cannot do an analysis with the entire population. It's not possible. So that's why we take a sample. Now our aim is that this sample has to be as much as close to the true population. So that difference is given by the standard error. If standard error is huge, That means your sample mean is far away from the true population mean. That means your sample is not a good representative of your population. But if standard errors are less, that means you have a robust sample. Now, just to make things further more simple, say for example, in your respective college, you are doing a survey and just taking the height, measuring height of all the students of your college. And then we have samples, say 4 samples. So A, B, C, and D. Fine. Now, how do you differentiate between standard deviation and standard error? So standard deviation tells you, say a particular out of the 4 groups, you take say one height of one group, say B. So B group height, how much is it varying from the mean of the B group? Fine. So in B group, say you have 100 samples or say you have 50 samples. How does those 50 samples deviate from the mean of entire B? So that is your standard deviation. Fine. We are not talking about A, C, D, nothing. Only about a single sample, which is B. Now, standard error, on the other hand, what it does, it pools the mean of all these 4 groups and then tells you how much is that differing from your true population mean. Fine. So this is the difference between your standard deviation and standard error. Then variance, as I said, it is the average of square distances of individual points from the mean. It is a more robust, for the ease of convenience, we use variance. But one drawback to it is that since it squares the standard deviation, so it gives added weight to the outliers. Say outliers are the extreme numbers in your data. Say, for example, if your data is mostly concentrating between, say, 1 to 10, and suddenly one number is appearing which is 80 or 70. Or some numbers are in negative quadrant. So then what you will do at that time? These are outliers. These are extreme observations. So sometimes it is convenient to drop them if they are few, but sometimes there is no option. So that time we have different techniques in which those outliers can be managed. And also because of the outliers, the data becomes skewed. Then next very important concept is coefficient of variation. Coefficient of variation is actually the percentage. So standard deviation expressed as the percentage of mean, and it's a unitless number. So it is also called as a relative standard deviation. So when you want to compare, in simple terms, if you want to compare the variation of 2 different data sets, in that time, this coefficient of variation usage is very, very important. That time coefficient of variation can be used. And the CVAR, sometimes it's called a CVAR, and it's most commonly used in financial markets, stock markets, to check the better risk return of different investments. Okay, because we say coefficient of variation makes it easy for us to assess the risks of any kind of investments. Then coming to the last part of this descriptive statistics, which is measures of shape. So we have skewness and kurtosis. So when we say the data is normally distributed, so normal distributed data looks like a bell-shaped curve, which is a symmetric distribution wherein mean, median, and mode all are concentrated at the same point in the center, dividing this hyperbola into 2 parts. Okay, now when the data is skewed, so we say it is positively skewed or it is negatively skewed. So positive skew means when your skewness is greater than 0, and negatively skewed means when your skewness is less than 0, and it is skewed on the left side. Fine. So kurtosis, on the other hand, gives you the peakedness or the flatness of the curve. So if it is highly peaked, it is called as leptokurtic. If it is mediumly peaked, it's called as mesokurtic. And if it is flat, it's called as platykurtic. And the ideal kurtosis value for a normal distribution function is 3. Now, these are some of the codes that I have given for calculating or knowing. You see, we use different types of softwares. We use R, we use Stata, we use SPSS. So I think SPSS is most commonly used nowadays. But in social sciences, we mostly use R and Stata. And there we have to use these simple codes like summary and data file name, and it will give you the entire summary of your data. Summary means your descriptive statistics, your mean, your median, your mode, your range, your minimum maximum values, and in stata just simply you have to put summarize or sum. And in statistics you have to, since it's a menu driven code, menu driven software, so you have to go to analyze, then a drop down menu will come showing descriptive statistics, and from descriptive statistics you have to choose descriptives, and it will give you the list. But in R, we need to first install certain libraries, which is called as library pastex and library psyche, to get the data in the tabulated form and for multiple groups. Then coming to the next, which is graphical analysis. So graphical analysis, as I said, I just want to give you some brief about what kind of charts can be used in what situations. So graph selection. So graph you choose will depend upon the type of the data that you have and the objectives you're trying to achieve. Okay, but remember that graphical analysis is not limited to charts.
Mom got disconnected. She will join soon. Please be with us. Ma'am, please share your presentation.
Ma'am, I
Yeah,
just
well,
want to know till where I was there online, just to
uh,
continue from the same point.
anyone from participants, can you please help, ma'am?
Because I didn't know that I have disconnected. I was just speaking.
Uh, Ma'am, can you start the slideshow? They
Yeah,
will
yeah,
help
sure,
you.
sure. Yeah, just please let me know from where I have to continue. What was the last thing that
Participants,
you
please.
heard?
Ma'am, can you move the sliders, please, so that they get an idea?
Yeah, yeah, yeah. Did they have the graphical analysis which I talked about?
Graph selection under graphical
Yeah, yeah,
analysis.
yeah.
Okay. Then this one, inferential statistics.
Yes, ma'am.
Okay, fine. Okay, then I was here
Ma'am,
to
please
start with the parametric.
start the slideshow.
Oh,
Yeah,
can
yeah,
you see
please.
the slides moving?
No, no, ma'am. Ma'am, please share the entire screen. You have shared the window.
Oh, just wait a minute. Okay, is it okay now?
Yes, ma'am. Can you please start the slideshow? Yeah, yeah, perfectly fine. Ma'am, please continue.
Yeah, so shall I start from this parametric tests?
Biometric testing. Yes, ma'am.
Okay, okay, okay. Fine. So please keep on responding in between because I don't know whether I'm still there or not. Okay.
Okay, sure.
Okay, thank you. So let's continue with the parametric tests. As I said, we will be starting with the t-test and then we will move ahead with other types of parametric tests. So the key assumptions behind using parametric tests is that, first of all, as I said, normality. Normality is very important. That means the data has to follow a normal distribution. Then homogeneity of variance. So what does this homogeneity of variance means? In simple layman language, it means that your dependent way, of course, in a data, you have a dependent variable and you have set of independent variables. So this dependent variable, the variance in that dependent variable, that means the dispersion of that data in the dependent variable, has to be same for all the independent variables in the model. This is the simple meaning of homogeneity of variances. And that is why by using F-test also or ANOVA also, we try to measure the homogeneity of variances. Okay, then independence of the observations, and we use interval and ratio scales. As I said before, these are the powerful tools to use. And if all these assumptions or any one of those assumptions is violated, then either you have to transform the data or we have to use the non-parametric tests. Now, what are the most common types of parametric tests used? So we have, for comparing means, we have a one sample t-test, we have an independent sample t-test, we have a paired sample t-test, and we have ANOVA. And then if you want to examine the relationship between the variables, so we have Pearson's correlation, wherein we want to check the degree of linear association between the variables. Or if you want to see the how your independent variables impact the outcome variable, that time we have to use the regression analysis. And for assessing the variability, we have F-test. As I said, it is used to compare the variances between two data sets for testing the homogeneity of variances. Right? So one by one, we will go. So first is the t-test. T-test has three types rather: an independent t-test, a paired t-test, and a one sample t-test. So an independent t-test is used to compare the means of two groups, okay, to determine whether there is a significant difference between them or not. It can be any two groups wherein you want to compare. Fine. So are these two groups meaningfully different, or differences just due to some random chance that we do not know? So we have to prove it. We have to get some empirical estimation for that. Then You have paired t-test. Paired t-test is mostly used for the same set of data, but before and after. So say, for example, you all people are attending this training program. Say you were evaluated before attending this training program and you got certain scores. Now, after attending this 21 days refresher course, you will be evaluated again after 21 days. And so for same number of people, you will have pre-data and post-data to check whether this particular trading program has altered your scores. That time we can use pair t-test because the people are same, just the time periods are different. Then one sample t-test is mostly used when you have to see the difference between the sample and the true population. So as I said, now giving you some more examples. Independent t-test, when you want to see if income in two different postal communities varies significantly based on a location or not. Pair t-test, as I said, they're used mostly for before and after interventions of a program. And one sample t-test, if you want to compare, say, for example, average education levels or literacy levels of the youth in a particular fishing community, how significantly it differs from the national average. Okay, so national average here is the population value and your sample values are your average literacy levels of the youth. So that time we use one sample t-test. Now, coming to ANOVA, the most used tool. So ANOVA means analysis of variance. So it is a statistical test which is used to compare more than three means across more than three groups, and there is any significant difference between them or not. So when to use ANOVA? So we use when you have a single dependent variable, that too measured on a continuous scale, and you have one independent variable with three or more groups. That means your independent variable is categorical. So one dependent variable which is on a continuous scale and one independent variable which has categories. So this is the best scenario in which we can use ANOVA. And of course, ANOVA is a parametric test. It's a robust test. So it needs to follow the assumptions of normality and homogeneity of variances. Fine. Then, to test the hypothesis about the group means, that's why we use it, and to understand how these categorical variables or factors affect the dependent variable or the continuous outcome variable. Say, for example, we want to check the differences in aspirations, youth aspirations across regions, religion, caste, gender, or type of respondents. So how these categories, that is region, religion, caste, gender, affects the youth aspirations. So this is also a perfect example of doing ANOVA. Now you have different types of ANOVA. One-way ANOVA, two-way ANOVA, repeated measure ANOVA, and factorial ANOVA. Again, you have another category called as bivariate ANOVA, univariate ANOVA. So what does these mean? Okay, am I still here?
Yes, ma'am.
Hello? Okay. So one-way ANOVA means, so when we talk about one-way ANOVA, two-way ANOVA, that means what is changing is your categorical variables or your independent variables are changing. Your dependent variable is one only, but your number of independent variables change. Fine. So when you have one dependent variable and one independent variable with multiple categories, it is a one-way ANOVA. When you have two categorical independent variables and their interaction that you want to study, that is a two-way ANOVA. The repeated measure ANOVA means when you want to compare multiple measurements of the same subjects under different times. Okay. And factorial ANOVA evaluates the interaction between multiple independent variables. So here, as I said, when you have one dependent variable, one or more independent variables, it is a univariate ANOVA. When you have one independent variable factor with multiple levels, it is a one-way ANOVA. But bivariate ANOVA is when you have two dependent variables. And then independent variables can be one or more. That depends. So here, whenever you will hear the word this univariate and bivariate and multivariate, we are talking about the levels of dependent variable. And when you talk about one-way ANOVA, two-way ANOVA, we are trying to see the changes in the categories of the independent variables. Say, for example, in the design of the experiments, we have CRD, RBD, LSD. So when we talk about CBD, it is a one-way ANOVA. When we talk about RBD, that means you're introducing one more treatment. So it can be treatment and then another treatment can be time period. Another treatment can be the type of the stock of the fish. And another variation can be in the ponds in which you're stocking the fish. So there they will be categorized into two-way ANOVA, or wherein you have to take multiple categories of the independent variables. So please don't get confused. When there is a term called as bivariate, that means you have two dependent variables. But when you use one-way ANOVA, two-way ANOVA, that means your independent variables have multiple numbers or levels. Now, example I will give, how different fishing zones affect fish catch. So you have one dependent and one independent. So that is your univariate ANOVA. So what is your dependent variable here is fish catch. What is your independent variable with multiple categories is zones, because zone will be ABC, of course, or XYZ or whatever name is there. So you have here univariate ANOVA, or we can say one-way ANOVA, because you have one dependent, one independent variable. Now, how different management practices affect both fish catch and income of the fishers? It is a bivariate ANOVA. You will say, ma'am, how? Because you have two dependent variables, which is your fish catch and income. And what is your independent variables with categories is your management practices. Okay. Then third example is studying effect of fishing zones on fish catch. So fish catch is your dependent variable and independent variables are zones. So you have one-way ANOVA. Then studying the effect of fishing zones and fishing gear types of the fish catch. So again, here dependent variable is only fish catch. So you have one dependent variable, but independent variables are two. First is fishing zone 1, 2, 3. Another is gear type. That is nets, traps, or hooks. Fine. So here we will use two-way ANOVA, because two-way ANOVA also gives you an interaction effect. That is interaction effect between your fishing zone and the type of gear that you're using to catch the fish. Is this clear? So here, next is when we do not have a normal data, what to do? So we check for outliers, we try to transform the data, and then if nothing happens or nothing seems to be okay, then we go for non-parametric tests. Now, what are the non-parametric tests? They're flexible. They don't have any kind of an assumption. Okay, so they don't strictly tend to follow a normal distribution, and we don't care about the population info. Any shape or any mode of the data will work, and null hypothesis is free from the parameters, because here we will mostly concentrate on median or mode. So it works both with the variables and attributes, and mostly when we have data on nominal and ordinal scale. It is not as strong as a parametric test, but we get the job done. So as I said already, the non-parametric tests play a very crucial role, especially when assumptions for the parametric test do not hold. And of course, it is very useful when the data is on the ordinal scale and when distributional assumptions of the parametric tests are violated and they do not assume a specific data distribution. So when to use a non-parametric test? When data violates the assumptions of normality, then when working with the small sample size, then when dealing with the ordinal or the nominal data, that means if your data is ranked, and then when data is dependent or conditional on one another, and when the data does not depend on any distribution of the population. That means the data can be skewed, jagged, or plain weird also, but still you can use a non-parametric test. Now, which tests to choose? So when the data is following a normal distribution, that time you have paired, unpaired both. Then is paired, under the paired we have again two groups and multiple groups. So when you have two groups under paired, which follows a normal distribution, which is t-test, multiple groups is ANOVA. For the unpaired, again we have t-test, because this t-test, first t-test is paired t-test. Second test is independent sample t-test. And multiple groups, of course, we have ANOVA. But coming to the non-parametric side, not normal side, we have the counterparts of all these tests, which we will discuss one by one. So first one is Wilcoxon sign rank test. It is actually a counterpart of a dependent sample t-test, or we can say a paired t-test. So when you use a paired t-test, which is mostly used for before and after the after studies, there we use the Wilcoxon sign rank test, which is nothing but it takes into consideration the ranks in the data, And based on the median of those ranks, we make the conclusions. Then next is the Friedman test. Friedman test is actually a counterpart of the repeated measure ANOVA. Okay, so it was developed by Milton Friedman, and it evaluates the differences across multiple related groups. Say pair t-test is for a single group before and after. But what if you have multiple groups and you want to check before and after, or you have a panel of judges who are judging a common product together and giving their multiple opinions at multiple periods of time. So that time Friedman test is most commonly used, and say comparing the performance of multiple products rated by same panel of judges, testing consistency of ratings among judges across different subjects, or you want to evaluate whether fish catch varies when fishers use 3 different types of gears. So this kind of, or sometimes, all of us are involved in doing online data collection or surveys. We have monkey survey tool, we have Delphi technique. So what we do, we take a panel of experts and we give them certain kind of indicators which they have to rank based on some information. Then after first round is complete, then you pool the results and again send it to all of them and tell that now, do you still want to keep the ranks as such, or you want to change them based on certain information? Then second round also you will get the results, the third round. So based on that, when you want to test whether these results which are coming in a loop back to us, whether they are robust or not, so that time we use the Friedman test. Okay. Then you have man-with TU test, which is a counterpart of a simple independent t-test, wherein you have 2 groups and you want to check the difference between the 2 groups, but not for their mean. Because in t-test, what is the hypothesis? That there is a significant difference in the sample mean of these 2 groups. But here we don't talk about mean because this is a non-parametric test. We talk about median values. This is the only difference between the 2. And of course, as I said, we have mostly ordinal data here in terms of any non-parametric test that we use. And what are the examples? Most common applications: comparing satisfaction scores between the 2 groups. Say, for example, for you people, if you will take a pre-data and post-data, how much are you satisfied with this training program? So you can do a man-with TU test, because satisfaction is a qualitative variable. You cannot quantify satisfaction. Okay, then analyzing differences in response times for 2 groups exposed to different stimuli, then assessing test results of independent groups in a study, or opinions of men and women in a study. Mostly for gender studies, we use this man-with TU test. And then seeing the difference between a traditional fishing gear and a more modern technology-driven gear. Okay. Then you have another very important test, which is a Kruskal-Wallis Edge test, which is a non-parametric counterpart of ANOVA, one-way ANOVA. So we use it for the multiple medians, because we have a rank data and we check this for multiple samples. So we want to assess the equality of medians across 3 or more groups. So when to use Kruskal-Wallis? When your number of groups are more than 2. When the data characteristics, of course, they're not following any normal distribution and the data is ordinal. The sample size of each group should have at least 5 observations. See, one more important thing is that we need not have equal sample size for all the groups. That is also one of the advantage of this. Then observations must be independent both within and between the groups. Now coming to the post hoc tests. What are the post hoc tests? Post hoc tests are, particularly when you do the ANOVA or this Kruskal-Wallis test. So you know now that, okay, we are rejecting null hypothesis and there is a significant difference between the groups. Now, which groups differ from each other? That we do not know. So for pinpointing those differences among the group means or the medians, we have post hoc tests. And I have just enlisted few of them. In case of parametric, we use Tuckey or Duncan. And in case of non-parametric, the most common is Dunn's test. Okay, so you will have all the codes of this in R also, as well as you have these tests in. So though Dunn's test is not in SPSS, but Tuckey and other parametric post hoc tests are available in SPSS as well. Are you there? Are you guys with me?
Yes, ma'am.
Okay. So next is parametric and non-parametric correlation. Again, in the correlation where I told you we want to find the degree of association, linear association between two variables, we check for Pearson correlation, and non-parametric is Spearman correlation. So correlation only tells you the degree of linear association between the variables. Fine. So in case of Pearson, which is a parametric version, the data must be on a continuous scale and a quantitative in numerical form. It works on the raw data. And of course, it indicates the strength and direction of a linear relationship between the two variables. It is more, of course, more sensitive to outliers. So it is very important to check for the outliers in your data. But Spearman correlation, it is used in monotonic relationship. What do you mean by monotonic relationship? Some kind of a, we'll not say completely straight line, a linear relationship, but more or less close to linear, which will have certain waves and undulations. So there we can check. Fine. So linearity is not that strict assumption here. Then it must be used for both ordinal and qualitative variables, and it works on ranked values for the each variable. Okay, so based on ranks, it gives you the correlation between the variables. Then coming to the most commonly used analytical tool, which is your regression model. So when you have a classical linear regression model, it means it tells you the relationship between a dependent variable and one or more independent variables. And mostly regression has two important functions, or we can say purposes. First one is estimation. Another one is prediction. So it explains or predicts the dependent variable based on the values of the independent variables. So how the independent variables affect the outcome variables, that is decided by the regression analysis. Fine. So this is a typical simple linear regression equation wherein y is your dependent variable, your x is your independent variable, your beta naught is intercept, and your beta 1 is the slope coefficient. But what does this beta 1 indicate? It indicates the unit change in x will cause what change in y. Right? And of course, error term is there because this is a econometric model. It's a statistical model. That's why we always have scope for errors. And as you all know, it assumes linear relationship between x and y. And classical linear regression model always functions on OLS assumptions. And what are those OLS assumptions? I have briefly written here. I don't want to make it complex, but just to make sure that OLS estimations, that means ordinary least square estimations, are very important until and unless these assumptions are followed. If these assumptions are not followed, then your results will not be robust. Fine. So based on the type of dependent and the independent variable, we have different types of regression models that we use very commonly in our analysis. So I have written type of response. Response is your dependent variable. If it is continuous variable, and your type of predictors means your independent variables or X variables, fine, or explanatory variables as we say. So if your Y is continuous and your X is categorical, that time we use ANOVA, which I already explained. When your Y is continuous and your X is also continuous, so we use linear regression. But when your Y is continuous and the X is a combination of both categorical variable as well as continuous variable, that time we have two options. Either we go for ANCOVA models or we go for regression with dummy variables, which is similar. So you take a dummy variable also in your model. Dummy variable means categorical variable, a certain variable which has two categories or more than two categories. And then a continuous variable that can be any. Then if your response variable is categorical, so this is altogether a different universe. When your response variable is now categorical, say you have an adoption study wherein adoption is yes or no. Okay, or willingness to pay, whether you are willing to pay yes or no. So your dependent variable becomes categorical. So that time, if you have a categorical dependent and categorical independent variable, we use a contingency table or we use a logistic regression or a Probit-Norbit model. But logistic regression and probit regression also gives you a flexibility that if you have a continuous variable also in your independent variables, that time also you can use logistic model. Fine. So this is little bit more used in social sciences. So I will not go much deeper into this aspect, which is called as limited dummy dependent variables models. But here, this is important for you people to understand that when to use ANOVA, when to use a linear regression, and when to use ANCOVA models. Then will be my last slide since time is over. So different multivariate data analytical tools are there. So when you understand these basics of using parametric tools and non-parametric tools, then of course multiple regression I already told you. Then you have MANOVA. MANOVA again gives you a scope wherein you have multiple dependent variables. Okay, because in ANOVA you will use a single dependent variable. So MANOVA is, like I told you, bivariate ANOVA. Okay, wherein you have two dependent variables or two outcomes of a particular model. Then coming to the data reduction techniques, wherein you have cluster analysis, discriminant analysis, principal component analysis, then multi-dimension scaling, and correspondence analysis as well. These are data reduction techniques wherein, of course, what thing you want to study, it depends upon that, how to use it. So if you want to group your vast number of observations or variables into certain clusters based on some similarity. So that time we'll use cluster analysis. But when you already have certain predefined labeled groups, and then some more observations are coming, but you do not know in which group these observations will fit in, that time you will use discriminant analysis. And just to remind you, discriminant analysis is I'll say a counterpart to logistic regression as well. Okay. Then this principal component analysis, correspondence analysis, and multidimensional scaling is similar. It is a data reduction technique based on how much of data is explaining the more number of variation in the model. It will pool them into different principal components. Okay. And then present to you, because say sometimes we have 50 variables, so you can't deal with 50 variables, so it will make them into maybe 10 groups, or further reducing them to maybe 5 groups, and those 5 groups will explain the total variation in the model. So first component will explain, say, 70% or 60% of the variation, the second one will explain less than that, the third group will explain less than that. Fine. Then comes the factor analysis. Factor analysis and principal component analysis, mostly people confuse, but they're not similar because the purpose is different. Factor analysis, actually, it's also a data reduction technique, but here we have certain latent or hidden variables that explain the variation in the model. So it takes into consideration to highlight those hidden or latent variables which explain the total variation in the model. Okay, so how does this latent variable is having a correlation with your independent variables, which is explaining the impact on your outcome variable. So that is what the factor analysis does. So of course, these are a little bit more advanced, and I think more time is needed for each of these analysis. Each of this, which I have given in this slide, is a separate lecture. So just to give you a brief idea about the multivariate data analysis, I thought to just explain a bit of it. So I think that's all from me. And why data analysis is important is because without gaining the useful insights from your raw data, you cannot make any kind of meaningful conclusions, and neither it can help you with informed decision making. And solid analytical methods are very, very important for scientific rigor as well. Then what we have covered, just a recap: types of data, your primary, secondary, cross-sectional, time series, panel, pooled, and then different analytical techniques like descriptive statistics, graphical analysis, inferential statistics, then different parametric, non-parametric tests, and multivariate tools, just a brief about them. And what is the key takeaway from this is that you have to choose the right tool for the right data, and it is very critical to ensure accuracy, relevance, and credibility in the research. So I wish you all the best. And if you have any kinds of queries, you kindly ask or post on my email ID, which is given here. Thank you very much. I would like to take this opportunity to thank all the organizers for looping me